This lecture recording will go over Chapter 6, the skeletal system. In this chapter, we will be discussing the functions of the skeletal system, how to classify bones according to shape and compare the structures and functions of compact and spongy bone. In Section 6-3, we'll compare the mechanisms of intramembranous ossification and endochondral ossification. We'll describe the remodeling and homeostatic mechanisms of the skeletal system in 6-4, and in 6-5 we'll summarize the effects of aging on the skeletal system. Next, we'll name the components and functions of the axial and appendicular skeletons. Then we'll identify the bones of the skull, discuss the differences in structures and functions of the various vertebrae, and describe the role of the thoracic cage. In Section 6-8, we'll identify the bones of the pectoral and pelvic girdle, the upper and lower limbs, and describe their various functions. 6-9 will contrast the major categories of joints and link their structural features to joint functions. 6-10 will describe how the structure and functional properties of synovial joints permit the dynamic movements of the skeleton. And 6-11 will explain the relationship between joint structure and mobility as of certain representative axial and appendicular articulations or joints. And then in your textbook there's an additional section 6-12, the skeletal system's relationship with other body systems, which you can take a look at on your own time. So we'll start this chapter with the 5 major functions of the skeletal system, starting with support. Support is provided for the entire body by the skeletal system. Bones provide attachments for soft tissues and organs. The skeletal system also provides storage for calcium salts for body fluids and for lipids that are stored in the yellow marrow for energy reserves. Blood cell production occurs in the red marrow and results in increases in red blood cells, white blood cells, and platelets. The skeletal system provides protection to soft tissues and organs by surrounding them with the skeleton. For example, the skull is enclosed in the brain and the ribs are protected by the heart, protect the heart and the lungs. And last but not least, movement is in part a function of the skeletal system because the bones can function as levers. When a skeletal muscle pulls on the bones, movement can occur. So bone or osseous tissue is a supportive connective tissue that contains specialized cells called osteocytes. And the matrix consists of extracellular protein fibers and a ground substance. So that's kind of a review from our Chapter 4, tissues. About 2/3 of the weight of a bone is made up of calcium salts, like calcium phosphate, for example. The remaining 1/3 of the weight is collagen fibers. The bones that make up the human skeleton have 4 general shapes. On the top left, you can see long bones are exemplified by the humerus. They're usually longer than they are wide. And short bones, on the other hand, no pun intended, are about as wide as they are long, and the example here are the carpal bones in your wrist. On the right-hand side, you can see flat bones is the next category, the next shape. These are typically very broad, like the bones that make up the skull or the cranium, and perhaps the scapula as well. And the last category, the last type of shape, are irregular bones. And these are usually very complex in shape, and the vertebrae are a great example of an irregularly shaped bone. Some typical features of long bones are very well exemplified by the humerus. The first term I want to introduce you to, the diaphysis. The diaphysis, or the central shaft, has a marrow cavity in the center, and it's filled with bone marrow, which is a soft, fatty tissue. The epiphysis are the wider portions at each end, and they're covered with articular cartilage. Compact bone is densely packed and it forms the diaphysis. Spongy bone, on the other hand, sometimes is called cancellous bone, and it has projections of bone that are separated by space. It literally looks spongy. The periosteum is the outer covering of bone. The fibers of tendons, those that hold muscles to the bone, and ligaments, those that hold bone to bone, are attached to this periosteum. And the endosteum, endo means inside, so the endosteum lines the marrow cavity and spongy bone. Let's take a look at some microscopic features of bone tissue. And some of this, again, will be a review from Chapter 4. Now, the periosteum has two layers. It's pictured at the top left up here, being pulled away. It has a fibrous outer layer and a cellular inner layer. Both compact and spongy bone contain osteocytes that are located in lacunae, which are found between sheets of matrix called lamellae. Canaliculi are small channels that run through the matrix, and they connect the lacunae and blood vessels. Compact bone has these repeating functional units that are called osteons. And an osteon is made of concentric circles of lamella surrounded by a central canal that has blood vessels in it. Perforating channels allow for blood vessels in the central canals to be linked to other vessels. Now, spongy bone has no osteons. Instead, the lamellae are called trabeculae. So these are finger-like projections that make up the spongy bone. So some characteristics of compact bone include that it covers all the bony surfaces except for the articular surfaces where you're going to see spongy bone instead. Compact bone can tolerate a lot more stress than spongy bone if it's applied to either end of the long bone. So that's important. It can't be, that stress can't be applied to the side of the shaft. It's really designed to handle the stress in just two directions. Spongy bone, on the other hand, are found in the epiphysis. So this is where you're going to have joints or bones pressing on bones. So this is where you can have a little more give to that bone, and you want it to be a little bit more flexible. One of the advantages of spongy bone compared to compact bone is that it is less dense, and so it's much lighter. It's not as heavy. And so it reduces the work that your muscles have to do to move the bones and therefore the whole organism around. So let's review osteocytes, those bone cells. Osteocytes are the most abundant cells that you'll find in the bone, but there's other cell types present associated with the endosteum. So an osteoclast is one of those large cells that can secrete acid and enzymes, and they're going to break down the matrix. You'll find them mostly on the endosteum. Okay. And these are very important. You might think that secreting acids and enzymes breaking down the matrix of your bones would be a bad thing, but this is how you access or release your calcium salts and minerals through that osteolysis so that you can use them for other body fluids. Osteoblasts, on the other hand, you'll find these mostly around the periosteum, produce new bone through a process called ossification, and I'm going to be describing ossification for you in the next section. So mature cells that maintain the bone structure are called osteocytes, and so osteoclasts and osteoblasts are two types of osteocytes. And so that brings us to a checkpoint now. So feel free to pause the recording and see if you can answer this question about a shaft or the end of the bone. If you have a sample of long bone and it shows concentric layers surrounding a central canal. In section 6-3, we start talking about bone formation. So the growth of your skeleton as you might know, is going to determine the size and the proportions of your body. The bony skeleton begins to form about 6 weeks after fertilization. So it begins in utero, and it generally continues up to the age of 25 years. Now, during in utero development, cartilage is replaced by bone in a process called ossification. And there's 2 major forms of ossification. There's intramembranous ossification and endochondral ossification. So let me tell you about each one of those, starting with intramembranous ossification. So intramembranous ossification begins when osteoblasts differentiate from connective tissue stem cells within embryonic or fetal fibrous connective tissue. And normally this occurs in the deeper layers. The place where the ossification first occurs is called an ossification center. And as this ossification proceeds, new bone is going to branch outward and blood vessels will begin to grow into the area to meet the demands of those osteoblasts. At first, the intramembranous bone resembles spongy bone, and further remodeling will produce osteons that are typical of the compact bone, such as like your skull bones. Embryonic cartilaginous skeletal structures are replaced by true bone in a series of 5 steps listed here. And you can take a look at figure 6-5 as I discuss these 5 steps. So chondrocytes are going to enlarge in the first step, and the matrix will begin to calcify. When this calcification begins, it's going to close off those chondrocytes from nutrients, and they can die. So bone formation will start at the shaft surface. You can see right here, bone formation will start at the shaft surface, and blood vessels will invade the perichondrium. New osteoblasts will produce the bony matrix. Those blood vessels are going to invade, in step 3, invade into the inner region of the cartilage, and new osteoblasts are going to form the spongy bone at the primary ossification center. And the bone will then begin to develop towards either end of that bone. It's going to fill the shaft with the spongy bone, and you can see the holes here representing the spongy bone. In step 4, the osteoclasts begin to break down spongy bone in the center and form the marrow cavity. The epiphyseal plates, cartilages or plates at the ends of the bone will continue to enlarge in step 4 as well. And then last, in step 5, the centers of your epiphysis, the centers will begin to calcify. So these are your secondary ossification centers right here and here. The epiphysis will fill with the spongy bone, and the bone will grow in length from the epiphyseal cartilages, and the joint surface are covered with articular cartilage. When sex hormone production increases at puberty, bone growth will accelerate. Osteoblasts produce bone faster than the epiphyseal cartilage can expand, and epiphyseal cartilages eventually will disappear, or you may have heard of your growth plates closing. Adult bones will show evidence of the epiphyseal line where the cartilage once was, where that compact bone will meet with the shaft and the epiphyseal spongy bone. So the closing of the epiphyseal plates vary from bone to bone. Digits usually close early around age 11. Arm, leg, and pelvis bones will close later between ages 18 and 25. And this will vary from person to person and between males and females, mostly due to differences in sex hormones. Enlargement in the diameter of bones occurs as it's growing in length, a process that's called appositional growth. So the periosteum cells will develop into osteoblasts, and they'll produce more matrix on the outer surface of the bone. At the same time, osteoclasts erode the inner surface, and this will enlarge the marrow cavity. Normal bone growth and normal bone maintenance depend on a reliable source of minerals, especially calcium salts. Vitamin D is an important part of calcium metabolism, so that's a requirement as well. Vitamin A and C provide support for the osteoblasts, and growth hormones, sex hormones, thyroid hormones, and calcium balancing hormones are also essential to normal bone growth and maintenance. So we've reached another checkpoint. So take a moment and see if you can answer, during intramembranous ossification, which type of tissue is replaced by bone? This next section of 6-4 talks about bone remodeling. So bone, as you may have come to conclude from this last section, 6-3, is a very dynamic tissue. And besides support of the body, it's also very important for storage of tissues for minerals. So what this means is that osteoclasts and osteoblasts are still active even after that epiphyseal cartilage has closed. Normally their actions are balanced, meaning that osteons are built and reabsorbed at equal rates. But in young adults, remodeling is very rapid. In fact, about 1/5 of the skeletal mass is replaced each year. And this brings about appropriate stresses. So I'm using that term, appropriate stress. This is one of those reasons that you have phy-ed during elementary and junior high, and even in high school, because you need to expose your bones to appropriate stresses, because this will cause thickening and strengthening of the bone as a response. If you have very little stress on your bones, like if you don't exercise, your bones will actually respond by becoming more weak and thin. So exercise is key to maintaining normal bone structure and strength. So the skeleton is the most important reserve for calcium ions, which is absolutely necessary for the proper function of the many systems, but especially for the muscular and the neural systems. The calcium balance in the body fluids is regulated by the parathyroid hormone, PTH, and the calcitriol, which comes from the kidneys, if you recall. And calcitriol and PTH are going to raise calcium levels in the body fluids. Now, appositionally, calcitonin from the thyroid gland will oppose these hormones and will lower the calcium levels in body fluids. And we'll discuss these hormones and their regulation of the calcium balance more in Chapter 10 when we talk about the endocrine system. Now, despite its strength, bone will crack or even break if it's subjected to extreme loads, sudden impacts, or stresses from unusual directions. So these fractures are named by external appearance, the site of the fracture, and the nature of the break. And I think your textbook has a nice little sidebar section about the different types of fractures. But I want to talk about how bones heal. So bones usually heal as long as the blood supply remains and the cellular components of the endosteum and periosteum survive. So here are the 4 steps in the repair process, which may take between 4 months to over a year. So let's take a look at a picture as we discuss these 4 steps. In step 1, the fracture will result in a broken blood vessel, and this will cause a blood clot called a fracture hematoma to form. This closes off the blood supply and can lead to the death of osteocytes. And if you have a death of osteocytes, you'll have dead bone on either side of the fracture. Cells of the periosteum and endosteum will collect here at the fracture and develop an external callus, which develops hyaline cartilage, and an internal callus, respectively. The osteoblast will replace cartilage with spongy bone, and spongy bone is replaced by compact bone, leaving a slightly thicker spot at the fracture site. And in step 4, this slightly thicker spot is slightly exaggerated by that illustration, but you get the point. So aging does have an impact on the skeletal system, and one of the conditions that can result from aging is called osteopenia. This is when you have inadequate ossification that naturally occurs as part of the aging process, and this starts between the ages of 30 and 40. What happens is osteoblastic activity slows and osteoclastic activity either maintains its usual pace or even increases. Sometimes osteopenia can accelerate to the point or can develop to the point of osteoporosis. Osteoporosis is the loss of bone mass that will impair normal function and can even lead to more fractures. And osteoporosis is more common in women and typically will accelerate after menopause. This is usually due to the decline of circulating estrogens. And we've reached the last checkpoint of this recording. I wonder, can you answer this question without looking back in your notes? Try to do this from memory. But would you expect the arm bones of a weightlifter to be thicker and heavier than those of a jogger? And tell me why. So after you answer that question, you can go ahead and start the next recording.